The gallery closed Chapter 8, each density a record of a construction. Chapter 9 puts those densities to work. Pass a random variable through a function and ask what distribution comes out. The answer must be derived, and deriving it is this video's whole business. In this video, we meet the master tool, the CDF method. Describe the event that g of x lands at or below y and integrate the density over it. We use it to pay a debt from last video. The square of a Rayleigh really is exponential. And when g is monotone, the whole method collapses to a single formula. Engineering transforms signals frequently. Amplitudes get squared into energies, voltages get scaled and shifted. Each transform drags a distribution along, so take a continuous random variable x and a real-valued function g. The picture is the one from Chapter 5, and outcome omega lands on the first real line at x of omega, and g carries it to a second line. The composite arrow is a new random variable, y equals g of x. For discrete x, we derive the PMF of y by regrouping masses over each preimage. A continuum has no masses to regroup, so events must do the work. The probability that y lands in a set S is the probability that x lands in the preimage of S, the set of inputs u where g of u falls in S. That is the set theoretic preimage from the video on functions, back after a long wait, and finally load-bearing. And a probability about x we know how to compute. Integrate the density of x over the preimage. Now specialize. Take S to be the half-line at or below y. Then the event y in S is the event g of x at most y, and its probability is, by definition, the CDF of y at y. So the recipe has two lines. First, describe the event g of x at most y as a set of x values. Second, integrate the density of x over that set. Every derived distribution in this chapter starts from these two lines. Let the method earn its keep. Last video introduced the Rayleigh density as the amplitude of a fading channel and stated, without proof, that its square is exponential. Take x Rayleigh with sigma squared equal to 1, so the density is u times e to the minus u squared over 2 for u at least 0. Let y be x squared, the energy of the fade. Fix y positive and run the recipe. The event y at most y is the event x squared at most y, which puts x between minus root y and root y. But a Rayleigh variable is never negative, so the lower limit rises to 0. The integral runs from 0 to root y, the shaded area under the density. Substitute v equals u squared. The differential v is twice u, exactly the factor sitting in the integrand, and the integral collapses. F of y at y equals 1 minus e to the minus y over 2. Look at that function. It is the exponential CDF from Chapter 8 with parameter 1/2. The square of a Rayleigh random variable is exponential. The promise is kept in 4 lines. And notice what the method needed from g, nothing beyond the ability to describe one event. One caution before we go on, continuity of x promises nothing about y. A function of a continuous random variable can be continuous, discrete, or neither, so we study structured cases, and the friendliest structure is monotonicity. A function is monotone increasing when larger inputs never produce smaller outputs. x1 at most, x2 forces g of x1 at most, g of x2. For such a g, the event g of x at most y is everything to the left of a boundary. The preimage of a half-line is a half-line. The boundary is the supremum of that preimage, and the CDF of y is the CDF of x evaluated there. Why a supremum? Because a flat stretch of g sends many inputs to the same output, and a jump of g can leave the preimage of a point empty. Taking the largest point of the half-line's preimage handles both at once. Watch the threshold climb. As y rises, the boundary glides to the right, and f of y grows with it. The gentlest instance, x uniform on 0, 1, and y twice x. For y between 0 and 2, y at most y means x at most y over 2, so fy at y is y over 2. The density of y is 1/2 on 0, 2. The rectangle stretches to double width and half height, and the area stays 1. An affine function of a uniform random variable is uniform. What if g is monotone decreasing, so larger inputs produce smaller outputs? The same argument runs in a mirror. A high threshold on the output is now cleared by small inputs, so the event g of x at most y collects everything to the right of a boundary. That boundary is an infimum, and the probability of landing at or beyond it is 1 minus the CDF of x there. The infimum plays the same guardian role the supremum played, absorbing the flats and the jumps of g. Swap supremum for infimum and f for 1 minus f. Nothing else changes. The key idea of this video, to find the distribution of g of x, describe the event g of x at most y as a set of x values and integrate the density of x over it. Next video, we differentiate this answer and the change of variables formula falls out.